This is problem 7-21. It's on page 350. An air standard cycle is executed in a closed system with 0.003 kilograms of air, so basically 3 grams, and consists of the following 3 processes. 1 to 2 is constant volume heat addition from 95 kilopascals and 17 degrees Celsius to 380 kilopascals. 2 to 3, let me put it down here at 380 kilopascals because I'm going to need some space. There we go. State 2 to state 3 is an isentropic expansion. So delta S equals 0 expansion to 95 kilopascals. And then 3 to 1 is a constant pressure heat rejection to go back to state 1. Okay? To the initial state. We're supposed to show the cycle in PV and TS diagrams, calculate the net work per cycle in kilojoules, and determine the thermal efficiency. They didn't seem to give us much information to go on, did they? Well, it's actually enough. Now, we've talked about several cycles so far. We've talked about the Otto cycle, we've talked about the Carnot cycle, of course, in chapters 5 and 6, and we've talked about the diesel cycle. This is none of them. This is just an arbitrary cycle so that we get used to cycle calculations. And also, I want you to have an appreciation for the importance of the PV and the TS diagrams. That's why they've asked us to create them. So let's start off with what we know. Let's see, let's analyze the process from state 1 to state 2. Let's start there. Now, the first thing that you probably think of when you see this, you see pressure, volume, and temperature seem to be running around here. So you probably think, ideal gas law. Right? The equation you're probably the most comfortable with so far. And you can use the ideal gas law. It may be useful, but let's try to draw the TSM PV diagrams as we go along and see what we can come up with. So let's start off also with a PV and TS diagram. So pressure versus volume and temperature versus entropy. Now, it doesn't really matter where I start. I'm just going to put a point to indicate state 1. Okay, and then I'm going to put as much information around state 1 as I can. For example, I know that state 1 is a constant volume process. So when I move from state 1 to state 2, I know I'm going to be moving along a vertical line. I don't know if I'll be moving up or down yet. We'll figure that out in a minute. I don't know the volume in state 1, but I might be able to get at it. In fact, let's see, we know, what all do we know? Well, we know the pressure in state 1, don't we? Look, it's 95 kilopascals. We were told that. Right? So we use that. We know the temperature in state 1, 17 degrees Celsius. Now, 17 degrees Celsius is going to be inconvenient because if we have to do any isentropic calculations, then the temperatures will have to be in absolute units. So 17 plus 273 gives us a nice round temperature of 290 Kelvin. So let's just use Kelvin for our temperature axis. We don't know the entropy. We may be able to get at the volume. In fact, I think we could. Wouldn't the specific volume in state 1 from the ideal gas law be RT1 over P1? Right? We have P1 and T1. So we can calculate specific volume. In fact, the gas constant for air is 0.287 kilojoules per kilogram per Kelvin. The temperature in state 1 is 290 Kelvin. Yeah, we got that earlier. And the pressure in state 1 was 95 kilopascals. Now let's see, a kilojoule is a kilopascal times a cubic meter. So the kilopascals will go away, the Kelvin go away, and we'll have cubic meters per kilogram, which is appropriate for specific volume. In fact, the specific volume in state 1, when you throw all this in your calculator, is 0.8761 cubic meters per kilogram. So now I can actually put a number here, 0.8761 cubic meters per kilogram. Okay? Trying to put as much information on the PV and TS diagrams as I can. Questions so far?
What was the conversion you did up there? Take kilopascal out?
Take kilograms out, or kilojoules out and put in kilopascals times cubic meters. Good question. Anything else? Looks like I need to zoom out a little bit, perhaps. There we go. Okay. Have we used up all the information? No, we haven't. Notice that state 2, if this is state 1, okay, then state 2 is at a higher pressure. So that tells me that I'll have to move up. Now, how do I know that I have to move up vertically? Because the volume's constant. So let's move up to a higher pressure. In fact, that state with higher pressure, state 2, is at, what was it, 380 kilopascals. And we moved up from state 1 to state 2. Okay? Now, we're going to move from state 1 to state 2 on the TS diagram. We know that the pressure increased. We know the volume remained constant. So should the temperature go up, go down, stay the same? What do you think? It should go up, right? If you look at the ideal gas law, if the volume remains constant and the pressure goes up, the temperature better go up, right? So, yeah, the temperature should go up. Should the entropy go up or go down, or what do you think?
Same. It should go up. Temperature goes up, that's an increase in entropy.
If the temperature goes up, does that mean there's an increase in entropy? We have to be careful here. Is there any heat transfer that occurs from state 1 to state 2? Yes, there is. QN. Heat carries what with it? Entropy. So we know that the temperature increases and the entropy increases because of QN. In fact, I'm going to make a note on this process that QN occurs so I don't forget it in either place. I'm sorry my figures are sort of running into each other, but hopefully you get the idea. Okay? Now there's one more thing we can note about this process. This is a constant volume process. That's V equals constant. Okay? This is a line of constant volume, which is dependent on the properties of air. Okay? So that's one more note. Not as important as the rest, though. So we've pretty much exhausted everything that happened from state 1 to state 2. The only other thing we could say is, what temperature does this go up to? What do you think? Do we have any way of figuring that out? Well, let's see. We said the volume is constant, right? Mm-hmm. We could do a couple of different things here. Let's try the way you might try to do you know how it goes, right? You have an idea of the way you're supposed to solve a problem, yet you know you've been taught something, and so you try what you've been taught. Let's try what you've been taught and see what happens. So QN is what's going to increase the temperature, right? So QN, if we did an energy balance, is there any boundary work? No, because the volume's constant. So an energy balance for this closed system would just say that the heat transfer changes the internal energy from state, or to state 2 from state 1. We could use CV T2 less T1, and then we realize we have a problem because we have T1, but we don't know QN and we don't know T2. So we have one equation and two unknowns. But if you look at the gas law, we know that the volume's constant, and so P1 V1 equals RT1, P2 V2 equals RT2, but V is the same and R is the same in both of these because V1 equals V2. And so what that means is that P1 over T1 equals P2 over T2. Right? Just putting these two equations together. Make sense? So we could actually calculate T2. So we'll use this in just a moment, but we could actually calculate T2. In fact, T2 is equal to, let's see, it'd be what? T1, P2 over P1. What do you know? The ideal gas law paid off out for us. Good. Paid off. So T1, you have to be careful though. We've used the ideal gas law, so we have to have T1 in absolute units. It's a good thing we switched to Kelvin early on. So 290 Kelvin multiplied by P2. P2 is 380. P1 is 95. And I forgot my Kelvin units in here. I didn't use kilopascals because they just cancel. And so this temperature is 1160 Kelvin. And so the scale here is going to be pretty bad, but you get the idea. T2 is 1160 Kelvin. Okay. Now we could actually calculate Qn. I probably did that somewhere here, but I don't see it right off. Oh, here we go. I'll need some calculator help because I calculated the total heat transfer in. Notice so far I'm dealing with specific heat transfer, not total. So let's finish off the transition from state 1 to state 2 by calculating Qn. Qn, we need the heat capacity for air at constant volume, and if you look that up in the back of your book, it's 0.718 kilojoules per kilogram per Kelvin. The temperature change is 1160 less T1 290. The units are Kelvin, so we get kilojoules per kilogram. So multiply that out if you would, please. 0.718 times the difference between 1160 and 290.
624.66.
11.
Yeah, 624.66.
Okay. So 624.66 kilojoules per kilogram. So see how we've pretty much beaten this process to death from state 1 to state 2. We found out everything we could about it. We don't have a cycle yet, we just have one process. We have 2 more processes to go. Okay, so let's continue. Now I've put all the information on the diagrams. We've recorded all of this, so we don't need these calculations anymore. So now let's deal with the change of state, the process from state 2 to state 3. What do we know about that process? Well, we know the entropy is constant, and we know it ends up at 95 kilopascals. So we know that it's going to end back at 95 kilopascals, but we don't know if the volume is going to increase, decrease, or what. It could be that I've got a mess over here and I'm actually going to have to come back this way. We'll see here in a minute. But we do know we're going to come back down to the same pressure as we were at in state 1. The other thing we know is there's no change in entropy. So we know we're going to move from state 2 along a vertical line. We're either going to move down or we're going to move up. I hope we move down. Otherwise I've got to make some erasing here. So let's see what happens. State 2 to state 3. Delta S equals 0. What does that suggest to you? What equation could we use now?
Oh,
It's
Isentropic.
isentropic.
We can use an isentropic. There's the first, second, and third isentropic equation. We can use any one of them that we want. Well, that's pretty convenient. In fact, let's see, from state 2 to state 3, we could write something like this. T3 over T2 equals P3 over P2 to the power of K minus 1 over K. Why would I choose that particular one? There's 2 others I could have chosen from that involve the relationship between pressure volume or temperature and volume. Why would I choose this one?
And volume constant to the whole heat.
But it's not necessarily constant. We don't know that. We're talking about the process from state 2 to state 3 now, not the constant volume process from state 1 to state 2. Why would I choose that one? Because we were told the final pressure. We were told that P3 is 95. We know P2 is 380. So I know these 2 things. I also know T2. That's 1160. Right? And so it just makes sense because this will allow me to calculate T3, and that's something I need to know. That'll tell me whether I need to go up or down. Right? If it's higher than 1160, I need to go up. If it's less, I need to go down. So let's see. P3 over P2 to the K minus 1 over K. T2, 1160, P3, 95, P2, 380 kilopascals, and K for what is this? Is this air? Yeah, it's air. So K is 1.4. So to the power of 1.4 less 1 over 1.4. Now, I'm sorry, I should have put Kelvin in there for the temperature. Anyway, the final temperature here is about 781 Kelvin. Whew, thank goodness, I get to go down. So there's state 3. And my drawing's not real good, but there you go. It's constant entropy, so that's a vertical line. Temperature goes down, so it should be below state 2. That makes sense. Well, how about the volume? Could I figure out what happened with the volume? Well, sure. We still have the ideal gas law. The ideal gas law still holds. It would say that the specific volume in state 3 is R T3 over P3. Notice we have T3 and P3 now. I'm running short on time, so I'm not going to plug in the numbers, but you know that T3 is 781. You know that P3 is back to 95 kilopascals. You know the gas constant for air. If you plug all these in, you'll find that this is 2.3594 cubic meters per kilogram. So that means it's off to the right. Does that make sense? It's at a higher number. So I need some space. This is 2.3594. It goes down. Now this is a line of constant entropy. Do I know how it should be curved or straight? I don't know. It doesn't matter. I just know it's going to move down to state 3. I guess I haven't been circling my state numbers, so I won't start now. How about from state 3 to state 1? Well, it's pretty obvious. They're going to be something like this, right? That's pretty obvious. And you know it's a constant pressure process because you're already at 95 kilopascals. In fact, we were told it's a constant pressure process. So from state 3 to state 1, we've got constant pressure. And so this will be a line of constant pressure. It has to end up where it started. This is a 3-process cycle. And I forgot my units here. It's just cubic meters per kilogram, but I put it on the axis, so that should be okay. All right. Now, from state 3 to state 1, let's see, since it's a constant pressure process, I think we've got everything, actually. I think we've got, yeah, we've got the final volume here. So we finished up the PV diagram. We don't know the entropies at state 3 and state 1 really, but we're only interested in entropy changes anyway. So I think we've actually completed the PV and TS diagrams. There is more to consider here. Let me just finish this up quickly. It'll only take us about 5 more minutes. Notice that from state 2 to state 3, that's where we're getting work out of the process. Notice that work is just this area. That's the work we get out, but that's not the net work, because from state 3 to state 1, we have to put in that much work. Does that make sense? This is the area on the PV diagram. So we need those two. In fact, we need the boundary work from state 2 to state 3, and I just called that W sub 2, 3, I think, in my notes. And we need the work requirement for state 3 to state 1. And if you notice, state 2 to state 3 is an isentropic work, okay? And we talked about different forms of boundary work. We did not talk about isentropic boundary work. Let me just give you the equation for isentropic boundary work. I won't derive it. It looks like this in this context. It'll be P3 V3 less P2 V2 over 1 minus K. Now, if you go back to the end of chapter 3 and you look at the boundary work equations I gave you, this looks exactly like the one I gave you for a polytropic process. The only difference is we've got a K instead of an N. All right? Not really surprised, since we showed last time that the polytropic equation looks exactly like an isentropic equation, just a different exponent. So that's what you end up with. Now we've got all the pressures and all the volumes from states 2 and 3. Right? We've got the pressures, we've got the volumes. We can plug this in. We know K is 1.4. The specific work you get out for 2 to 3 is about 271.93 kilojoules per kilogram. I won't show you all the details. I'll let you go through that since we're short on time. The work from state 3 to state 1 is even easier. Notice it's a constant pressure multiplied by a volume change, right? We just need that area. So it's just a P delta V calculation. If you do that, what you find is that the amount of work we have to put in is 140.91 kilojoules per kilogram. Okay? You take the difference between these two and you can come up with a net work. In fact, we don't need this anymore, so I'm going to erase it. The net amount of work we get out of one cycle is the mass multiplied by the net specific work, but that is the mass multiplied by the work we get out, which is from 2 to 3, less the work we put in from 3 to 1. Okay. Once again, you know the mass is 0.03 of a kilogram. You see the numbers for the specific work. The total work we get out of this is about 0.393 kilojoules. And to quickly finish this off, to get the efficiency, the thermal efficiency is the net specific work divided by the heat input. We've already got the heat input. If you take the difference between these two, somebody throw that into your calculator, please. Just take 271.93, subtract off 140.91. It's going to be pretty close to what, 60 plus 131?
I think, which one again, 270 then,
I think I've got it.
131.02.
Thanks. So that's just the difference between those two, right? That's the net specific work divided by Qn. Qn, we put in 624.66 kilojoules per kilogram. Take the ratio of those two on your calculator, please. What do you get?
0.2097.
So about 21%. So the thermal efficiency of the cycle is about 21%. Okay. There's more details in my notes that you may want to look over. And of course, I'll post these example problems. But anyway, that's our calculations for problem 21.